announcement that today I will be discussing about the stoichiometry and chemical reactions. And for those who already have studied chemistry a bit before, that's the good news for you guys, that it will be very much similar to what we have done, and the slides are already available on the canvas, so you already have a look at it, I'm guessing, and you have seen that it's quite simple things. But what will be the difference here is the calculation, that we will be doing a more detailed calculations to find out the things that will be involved in the chemistry and in the reactions. But let me go to this. Okay, I cannot. Okay, wait a bit. I cannot. All right, here. Okay, so this is today we'll be talking about that stoichiometry and chemical reactions, and for this stoichiometry, anybody has any idea, or does your microphone is muted? No, it's not. Okay, anyway, so anybody has any idea of what is a stoichiometry is? It is a very verbose name, right? It's a verbose name of balancing equation, right? When we balance the equation, that is called stoichiometry. Not only balancing the equation, having the perfect ratio for that reaction to occur is that stoichiometry. So having the perfect ratio means we have to make sure that the reactant and product are having in perfect ratio. If there is no perfect ratio, the reaction will occur, but we do not know to what extent. We cannot predict, or we cannot calculate whether how much the reaction or the product will be produced or reaction will be finished. We do not know. That's why stoichiometry, or even if the ratio are not maintained, the reaction may not even start. It probably will not start even. So that's why stoichiometry is important, and we have to keep track of the stoichiometry. And of course, chemical reactions are the reactions. Again, the term reaction is a very, to us, when we say reaction, we always understand that, I mean, we mix few things together and then we are expecting something else to be produced. But when we say reaction in daily life, what do we understand about the reaction? That means do not react in that way, or he reacts that funny way or in a bad manner. Do we understand that a few things are mixed into him and then the outcome is coming out? Probably, I do not know. But when we are talking about the reaction, it always gives us an vivid imagination that somebody is doing some reaction. All right. And nowadays there are trend, the reaction video. Something has happened a long time ago, and then people are coming on and they say, okay, I'm doing a reaction video on those things. Anyway, what the reactions going on, there is no test tube there. Okay, so the learning objective for us today is to know or to find out the ways to establish a balanced equation. First and foremost, we have to balance the equation. First thing, if no balancing the equation, we cannot proceed to study that reaction anyway. All right. First of all. Second is use the mole concept. All right. We already know how to use, figure out the number of moles and from grams, and how do you find the gram and number of moles from the different elements. We are already comfortable with that, and then we will be using this number of moles, the concept of mole, to find out the mass that will be produced, or mass that we should have to provide for that reaction to attain the stoichiometry. Okay, because when we are adding 1 kilogram or let's say 1 gram, 10 gram, 5 gram, the reaction. Once again, I think I'm repeating this, but I'll keep repeating this thing because it's important for us to understand that we are adding 10 gram, 5 gram, 10 kilo, 10 ton does not matter. It matters the number of moles. When a reaction is occurring, number of moles are the thing that has to be considered. But the problem is when we take from the bottle, right, or from the jar, one chemical, we do not directly measure the number of moles. What we measure is the weight or the mass of that compound or that product. So we ourselves, we do not see the number of moles directly, but what we see is the weight of that compound. And from that weight, that's why this is our soft skill we have to use the to convert that mass to number of moles, because the reaction occurs based on the number of moles, not based on the weight. So this is important, and we have to always remember this thing. That is why we have to go back and forth of the number of moles and gram and then volume percentage, weight percentage, all those things. But number of moles is important. And when number of moles is coming, Avogadro's number is coming along, right? So Avogadro's number and number of moles and all those things are will be important for us to balance the equation. And another thing is when the reaction is occurring, A and B are doing the reaction, right? A and B are doing the reaction. I have a lot of A, but I have a limited number of B. So in the reaction, we see that the reaction is occurring, producing A plus B, and then C plus D is being produced. But the reality is I have a very small amount of B in that. We will go there, right away. But we have a very small amount of B. That means the reaction may even finish before it starts. That means we have to have healthy amount of both the reactant A and B. That means if we do not have both amount perfectly, is enough amount, that the reaction will not proceed. And that is why when we do not have enough of B, that B becomes limiting reagent. So our aim for this learning of this stoichiometry is how do we find out which one is the limiting reactant? To find out which one is the less amount we have and which one will limit the reaction to proceed. That is the limiting reagent. And afterwards, of course, we will have to have know the number of percent of yield, of how much the yield has been produced, the product has been produced. Okay. So stoichiometry in a more detailed way is the relationship between the amounts of reactant and product involved in the chemical reaction. All right. So to find out the amount between the reactant and product has been produced, we have to find put it into by the perspective of moles, number of moles. And when we are putting the number of moles, we cannot take 1 mole from the bottle or from the jar or from anywhere. We have to take from grams, so that we have to calculate the gram and then convert it to moles. And for chemical reaction, even though for this photo, we see that there are 3 or 2 different color, red to yellow to maybe yellowish color or orange color. So even though there are different color, different product are being produced, what is happening is the conservation of mass, the law of the conservation of mass is always maintained. That means whatever goes in, the same amount should come out. Okay, that is the law of conservation of mass. You cannot destroy a thing. You can just produce from one to another form. So the mass is always constant. Whatever mass is going in, the mass will come out in a product in a different form. Of course, product are the different forms. So in a different form, but the mass is always. So you have to maintain. If I add 10 gram of A and 5 gram of B, I will expect 15 gram of C. That is the law of conservation of mass. You cannot have a 10 gram of A, 5 gram of B, and only 7 gram of C, and then 8 gram is vanished or a vapor in that way. Yeah, vapor also has to be counted in that sense, that vapor has some mass, so vapor will be counted. So that is why that mass conservation of mass should always be established. And before we move to the chemical reaction, right, there are things that we have to consider of balancing the equation. And if we want to interpret the chemical reaction equations, we will see that for very simple cases, we have some other examples later on, but for simple cases, that iron and oxygen, iron is solid, oxygen is gas, and this is the subscript. Okay, it is subscript, and when we will be writing the chemical equation, we should always try to put this subscript to denote what is the physical state of those elements, of those component in the reactant and of course in the product. So for this case, I understand that iron is solid, oxygen is gas, and iron oxide is produced, or iron 2 oxides are produced, is in case in solid form. So iron and oxygen is iron 3 oxide, yeah. So iron and oxygen are produced. So for this case, we have to balance the equation for on the right side and left side are different, right? On left, we have only one iron, and for this case, iron is alone, so we can say it's one atom of iron, and here one molecule of oxygen, that means 2 atoms of oxygen on the left, but on the right the iron becomes 2 atoms of iron and 3 atoms of oxygen it produced. Now from this iron on the left, okay, this iron on the left, it is very much different from what we have in ferric oxide or iron 3 oxide here. All right, what we have here is iron 3. This is different molecule from this one. This is totally different from this one, and the same goes for the oxygen as well. Oxygen is the elemental, is a gas here, is elemental oxygen. It's just an atom of oxygen, but here it is not an oxygen, it's not an iron as well. So this is totally different. They have just converted to something else. So in this case, we see that there are 2 atoms of iron here, but there's 0, here is nothing. And here is 2 atoms of oxygen, but here is 3 atoms of oxygen atom. He's involved here. So where these things are coming from, if the mass of conservation of mass has to be established on both sides, they have to be the same thing, the same amount. All right, both sides, they have to be same amount of atoms. To balance the equation, we have to use these two we have to bring forth here. We would have brought it forth. But for this 3, how could we make it 3? If we would make it oxygen 3, it is not an oxygen gas anymore. It's totally changed. This is, we are coming, just next slide, we'll go to that, some rules for balancing the equation. But you cannot change the subscript for an chemical symbol. Okay, if we change the subscript of a chemical symbol, it is totally changing the identity of the chemical. It is not an oxygen, it is an ozone. It is ozone, O3. It is not an oxygen gas, and it is totally different than O2. Totally different. So we cannot just put this 3 here. To put this 3 here, or to make it balanced in both way, right? What can we do then? What can we do is we keep these 2 here intact, and then add this 3 in front. Add this 3 in front. So by this way, we'll have 6 atoms of oxygen. So 6 atoms of oxygen, if we have to balance on the right side, what we'll do is we just multiply by 2. So that 2 times 3, 2 and this 3 times balanced, it becomes 6. So if we balance this elemental oxygen or atom, then molecule, then we are getting very close to the balancing of the equation. And by this way, if we add 2 or iron becoming 4, so just add 4 in front of iron, and that makes the equation balanced. And this is a very simple way to find out the equation of, balance the equation. Another way, there is no perfect guideline for you to do the balancing of the equation. There are many different, possibilities that you can balance or we can balance, but there are some few steps that helps us to understand or try to balance the equation. We'll go to the next slide. But before that, what does this chemical equation tells us about? If we try to interpret, there are 4 atoms of oxygen and 3 molecules of oxygen gas. Now, when we say oxygen gas, oxygen cannot stay alone. It will be diatomic gas. So 3 molecules of oxygen gas means 6 atoms of oxygen. All right. There are many other diatomic gas. Hydrogen is there, nitrogen is there, chlorine is there. So there are the diatomic gases. Okay. So when 3 molecules of oxygen are added, that means 6 atoms of oxygens are there as well. And in that way, they are producing 2 molecules of iron 3 oxide or ferric oxide, Fe2O3. 2 molecules of them are produced. And also, if we look at this reaction, okay, if we look at this reaction, we see that reaction number 1 or equation number 1. Okay, it is always good idea to put the equation number. Maybe it will be 2 actually, and here it will be 1 because there are 2 different things. So in number 2, equation number 2, this is the number 2, right? So in equation number 2, we see that 4 atoms are used. But also there are 4 moles of iron have been used here. 4 moles of iron, that is 3 moles of oxygen gas, 4 moles of iron and 3 moles of oxygen gas. So in 4 moles of iron, there will be 4 times the Avogadro's number of iron atom. Okay, iron